now that we have electric fields and how they create forces on particles, we can start to mix it with kinematics. So let's do charged particle forces in motion. All right. It's interesting, and we like to write problems about it. So one thing about this is often we'll start with a uniform field. So let's make sure we all agree on what a uniform field means, okay? So I'll often say, oh, we have a uniform E field. So what that really means is everywhere you go in space, the electric field vectors look the same. It's the same magnitude, it's the same direction, etc. So if I say I have a uniform field pointing to the right, I might draw it like that, okay? That really means is that not just in the plane of the board, everywhere you go. It's just electric field vectors, they're always the same magnitude, they always point to the right. Let's look at it in the visualization lab. Uniform field is really important, so let's make sure you get it. The field is just the same everywhere. So here is a 3D view of the uniform field, and everywhere you go, the electric field is pointing up and to the right. And if I sort of spin it around and we turn it, we look in a different way, every field vector is now pointing down. Every field vector is pointing up. No matter where you go in a 3D space, the field vectors all point together. That's the idea of a uniform field. So if you're a charged particle in this uniform electric field, you're always going to feel a force along the field vectors. Okay, let's go back and finish the problem. But then another thing we'll do in these problems is that we'll have a uniform field, but only in a certain region. So I might say a uniform field exists on the positive x-axis or something like that. And what we're saying there is that in some region of space, we have a uniform field. But outside the region, we don't. Okay, so we play around a lot with uniform fields. We don't worry about how they were created, right? That's somebody else's problem. When we're doing these problems, we often just say there is a uniform field. Okay? So what is that going to do to a charged particle? So the charged So what does the charged particle feel? Well, by definition, it feels a force that's just proportional to the electric field, F equals QE. That's how we defined the electric field. So if you have a particle moving around outside the electric field, it doesn't feel anything. As soon as it enters, it'll start to feel a force, F equals QE. So it feels that, but it also obeys kinematics still. It's still true that the sum of the forces equals ma. That's still true. And it's still true that you can apply it in both directions. You know, you can do your x-axis kinematics, you can do your y-axis kinematics, and you can combine them and solve them. All right? So a uniform field is an interesting case because it's just like a gravitational field when you're near the surface of the Earth. When you say you're throwing a ball and you have gravity always pulling down at some acceleration, that's basically what you have with a uniform field. It's always pushing the charge in one direction. So let's just do an example problem just to get an idea. Let's say we have an electron here, and it is moving with initial velocity v naught towards a region of a uniform field. Okay? Out here it has no uniform field. It's field free. It's just coasting along, and then it's going to enter a region, a uniform field that looks just like that. So the question we could ask is how far in is this electron going to go before it gets bounced out? Let's convince ourselves that it's going to get bounced out. So when the electron is here, it has a charge of what? Minus E. So it's going to feel a force, F equals Q. It's going to feel a force back. Because the field is that way, the charge is negative, it's going to get pushed back. So it's going to have some high velocity, but it's going to slow down, and it's going to get pushed and accelerated back, and it's eventually going to come out. All right? So the question really is just how far in does it get? How far in D? So really what we want to do is apply 1D kinematics to this problem. So let's think. First thing you often always do is you just combine these two equations. The sum of the forces is ma, but the only force is QE. If we have this particle flying around, we're not worrying about gravity at all, then essentially you just end up with QE. The sum of the forces is QE equals MA. Okay? And we're doing a one-dimensional problem, so we actually don't care about the vector aspect of it. Everything is on the I-hat direction. So we can say the acceleration that this thing feels is, is what? Well, let's see. The acceleration is QE over m, but Q is the charge of the electron. Q is actually minus E, the fundamental charge unit. So it's actually minus E, the magnitude of the field, E, over m. Okay? That's the acceleration. And 1d negative means it's pushing back. There's your acceleration. And then you got to ask yourself, what kinematics formula do you want to use? We're not going to reteach all of kinematics, but whenever you had a case where you had an initial velocity and a final velocity and acceleration, you may remember you often used Vf squared equals V initial or naught, V naught squared plus 2 AD, where this is the acceleration and this is how far it goes. So in this case, we're looking for D. Okay? We want to know how far does it get in. It gets in until its velocity is 0. V naught is given in our problem, plus 2. The acceleration is minus EE over m, so I'll just put the minus right there, E over m, and then D is what we're looking for. Okay? So if you turn all this around and solve it, what do you get? You get this comes over here, all the positives work out, and you get that D, how far in it goes into the field must be m V naught squared over 2 times the charge times the electric field magnitude. M V naught squared over 2 little e times big E. So just a simple example of using the kinematics. Really the key to remember what a uniform field looks like, the fact that it's just F equals QE, combine that with the standard Newton's second law, and then apply the standard formulas you used in mechanics.